Hello, everyone, and welcome to today's JMP Academic webinar, Teaching Statistical Quality Control. I'm Ross Matusalam, an academic ambassador with JMP. I'm just here to host today and field questions in the Q&A. My colleague, Kevin Pochner, a fellow academic ambassador, is going to show us tools that you can use to teach common SQC methods, specifically control charts, process capability analysis, and measurement systems analysis. JMP's used heavily in industry for statistical quality control, and it's a great tool for teaching SQC as well, thanks to its graphical and interactive interface. And right now, Kevin's going to show us how to use the relevant tools in JMP, show us some examples you can use for teaching, and provide some tips for using JMP in the classroom along the way. Now, one thing to note before we get started is that we invite your questions throughout the webinar. Please use the Zoom Q&A window to submit your questions. You can use the chat for general comments to make to the group, but using Zoom's Q&A window helps us keep track of the questions and which ones have already been answered. And like I said, I'll be hanging out in the Q&A answering questions as we go along, and then Kevin should have some time to take some questions live as well. So with that, Kevin, are you ready to get going?
I am. You can confirm you see my screen?
Yep, looks good.
Okay, perfect. Okay, as Ross mentioned, there's going to be three primary topics that we're going to be covering. Control charts, process capability, and measurement systems analysis. Those are typically the topics in a quality control course. But before I do that, I want to point out some of our teaching and learning resources. And there's two purposes of these resources. One is to help you learn JMP and learn about all the capabilities and how the platform works, but also they're resources that you can direct your students to. So you don't have to spend your time sort of creating instructional guides and videos. We've got that material already created. So in the journal, there's links to them. I'm just going to pop them up in a second. And so the recording of this webinar is going to be posted on one of those sources there, and then you'll be able to get these links. So I'm going to just move. I've got the links already opened up. So I'm just going to step through those here. So if you're not familiar with our learning library, this is a set of short instructional guides and videos. And the ones that are going to be relevant for the topics we're covering today is this little chapter here on quality and process. I'm just going to open one up for those of you who are not familiar. Basically, there's a short video. They're usually about 2 or 3 minutes long. And they're the instructions on how you run a particular analysis. This one's for individual moving range chart. And then it also comes with a printed version of the instructions. Now, these are not meant to teach the statistical concepts for this tool. It's really about how you run this analysis in JMP. I mean, we sometimes interpret the data a little bit or talk about the different options, but it's really meant to be very brief and short. And so you just direct your students to these as you cover different topics in your class, so you don't have to spend time in class doing that or creating those materials. And you can see, I think we've got about 90 or so of these from various topics. We also have recordings of our webinars. That's where the recording of this webinar is going to appear. This is our academic webinar library. Another resource is our enhanced data sets. And these are a collection of data sets we've been posting up that have sort of an engaging storyline, a description of how the data was collected or how the experiment was run, what kinds of questions we're trying to be answered, what's the objectives of the analysis. And then it has a bunch of exercises which you can use to, well, you can use to either demonstrate in class or give out as an assignment to your students with JMP instructions. We have our case study library, and these are similar to the enhanced data sets, but they go a bit beyond because they actually demonstrate analyses as well. So each one of these will be, again, about a particular story in a particular industry or discipline. You'll see JMP being demonstrated. It'll even teach some statistical concepts. And then it ends with some exercises. So again, another resource that you can either use for demonstration or direct your students to. We have a free online course called STIPS. It's statistical thinking for industrial problem solving, very relevant to a statistical quality control course, or at least for that audience. And so there's about 30 or so hours of self-paced videos and quizzes and jump instructions and demonstrations on a variety of topics. We actually have a chapter on quality methods here. But what you might use this for is, if you can't fit everything into your lectures, know that we have some lectures already prepared. And so maybe you might start off your course and say, okay, everybody, let's go. I'm going to have you go through these 2 chapters on your own before we start particular topics. And so you've got some supplemental material that you can direct your students to enhance what you're doing. We actually have a free online course on statistical process control. And this is the courses we used to teach out in industry, or what we still do teach out in industry, but now we're making them online versions available for free. I don't know how many hours it takes this one to go through, but these are typically multi-day courses out in industry. So this one's covering control charts and capability analysis. We also have a bunch of other free on-demand courses. There is actually a course on measurement systems analysis. It hasn't been turned into this free on-demand yet. We're still in the process of doing that, but it is a course you can take. But these are the ones we have currently for free. So again, these are things where, well, you can use them to learn JMP if you feel like you need to get more proficient in the platforms. But again, you can direct your students to. So maybe you can have your students like, okay, I want everybody the first week or 2 of the class, go through this getting started with JMP so you can get everybody up and running quickly with JMP, and you don't have to spend your lecture time doing that. There's also a link where you can, if you're faculty, you can request the course materials. So that means you're going to get not only the data sets, but the PowerPoint slides that are used in those courses. And so this can actually help you put together your content and your material, so you can leverage stuff that we've already put together. And the last link in this journal for resources is our help documentation. And so we have a whole chapter on quality and process methods, and there's a discussion about every platform that we have in there. This webinar is just a little bit under an hour, so I can only give an overview of these platforms, but I encourage you to go to our help documentation, and this is where you can focus in on specific platforms to learn more about ones I maybe just gave an overview on, or ones I didn't cover at all. And in addition to explaining all the options and how you fill out the dialog box, sometimes you'll find example data sets that are demonstrated. You can find formulas and statistical equations of the methods and links to papers and all of that. So our help documentation is another resource. All right, so I just wanted to start you off with that, and in the journal will be links to all those things that I just showed you. All right, so I said we've got 3 topics. Let's start with control charts. So I'm going to demonstrate an individual and moving range chart. I'm going to demonstrate a X bar and R chart. Actually, I'm going to do an X bar and S chart. Well, both, I should say. That's dealing with numerical data with subgroups. I'm going to do some control charts on proportions and counts. I'm going to show you some, some ideas that you might want to think about for class demonstration. And so let's jump into these. Okay, so this first one, this food manufacturing process, this is actually one of our case studies. And let me open that up here. Now, this particular case study doesn't demonstrate control charts. It does lots of analyses, but the application is basically doing that. You're monitoring a food manufacturing process and trying to assess if how that process is performing. So it's a good example to use for control charts, even though it doesn't demonstrate it in the case studies. Okay, so let me just move this aside here. Oh, I just want to point out some numbers here we just have to keep an eye on. So this food production process is making yogurt. And so there's 8 different production lines, A, B, C, D, all the way to H. And basically, each time a batch of yogurt is made, the pH is measured. And this process, like almost all manufacturing processes, well, there's a target and specifications. And so you can see there with the the target and lower and upper spec are. So I'm just going to slide this aside here. All right. Okay, so the data is organized where each batch is a row, and then I've got the pH for each line. Now, these aren't related in the sense of, these are 8 different production lines, but it's just that is batch 1, batch 2, batch 3 for each of them, but it's not as if this number and this number are related. Okay, so when you don't have data that's in subgroups like we don't have here, there's no logical way to group these other than just each individual row. The most appropriate chart for this is an individual and moving range chart. And so you will find that's of course under our analyze primary menu and then under our quality and process menu. Now we have a tool called Control Chart Builder that acts like the graph builder. But for the purpose of teaching, you might find it better to actually pick the name of the control chart this way. So I'm going to use this menu as opposed to the control chart builder. So here's my individual and moving range chart. I'm going to put all of them in there. Oh, something I want to point out is every column in a JMP data table can have some column properties associated with it. So I'm going to double click here. And so one of the properties I set up was the spec limits. So I typed those in, and I also checked that little box right there. So whenever I make a graph, it's going to add those spec limits to the graph. Okay. So when I hit OK, and the other thing that's going to happen is if you have spec limits, it's also going to automatically run a capability analysis, but I don't want to focus on that now. So I'm going to close all that up. Okay. So right now we have the individual and moving range chart for every production line. Now, something you can do instead of putting them all in one report, this is a method I use a lot. I sometimes find it a little more convenient to organize your work, is you actually just put one of the lines in. Okay, so you're just going to get a report with one of the lines, and then under the red triangle, you set up the column switcher, and then now over here, I can just choose which one I want to look at, and it does it all from one view as opposed to having all these graphs stacked. You'll see it being convenient when you have lots and lots of variables. Oh, and something else you can do is I can choose, I'm going to take a guess at what it would be, but I can choose a min and a max here. I'm in the column properties, and I'm going to say retain axis settings. And then now when I click through, you see how the axis settings aren't changing, that min and the max. This would make it, I think, easier for comparison. Okay. Now, from this red triangle, I can open up the control panel for these control charts. And that gives me all sorts of options over here on the left. So for example, I can say, oh, let me shade the zones. And so now I'm going to get the, within 1 sigma, within 2 sigma, beyond, 3 sigma, color coding if that is helpful. Now note the spec limits, as I said, because I had that box checked, they're drawn on there too. And sometimes that's nice because remember, you're in this class, you're trying to get students to not confuse control limits with spec limits, right? So this could be an example where you're like, spec limits are one thing, and then control limits are another thing. And then you have the ability to teach that. Something else I can do is I can turn on the tests that you do to identify if there's a non-random pattern. I know we can visualize some of this, right? So for example, if we were going through here, I mean, everybody can kind of see that, or that one looks like a little bit, maybe it's a little bit of a shift up like that. But we can ask JMP to do these various tests. And if you don't know what those tests are, I'm actually going to open them up here. So even though there's a default set that has been developed indicating if one of these conditions occur, then identify that as an out of control situation, you can actually change these. So for example, these are short tests like, oh, if there's 9 points in a row on a single side of the center line, flag that. But you can change that, right? I can just go in there and change any of these numbers. So if I turn on all these tests, and I won't change the defaults, and I click OK, now as I move through these, you'll see those out of control conditions will get flagged. So this one here, that's number 6. That's 4 out of 5 points in a row beyond 1 standard deviation. What's this one here? 4. Oh, it's seeing some alternating, so that could be indication that some assignable cause there as well. Okay, got some beyond the control limits. Here's things like this happens a lot, right? Where like one's right on the edge of it, and do you use that to indicate or not? This one actually had a lot because it process drifted way up and then drifted way down. Okay, so the control panel is what allows you to pick some of these options, and if I just hit done, I can close that, and I'm just back to this one graph. Now, if you're very, very brand new to JMP, and you want to save this report to the file, then you click on this red triangle, save script to data table, and I want you to watch right here. You give it a name, JMP's going to pick a default, and when I hit OK, I can close it. So now that script was just saved. I've done other analyses, that's why there's other things up there. But if I click on the green triangle, it just opens it up again. Okay. I'm going to close this example, but before I do, just want to check in, Ross. You don't have a specific question?
Yeah, Kevin, we had one that just came in a few seconds ago. When and why might you change the default numbers in those tests that you showed?
Yeah, okay, so this is the whole concept of helping identify things that are random. And it's kind of like the concept of, oh, you know what it's exactly like? It's like the concept of a significance level in a hypothesis test. Like, do you want to be more conservative with your test, right? But now you're kind of affecting the type 1 and type 2 error, right? So if you change, say, instead of it being 3 sigma limits, let's say 4 sigma limits, well, you're going to make less type 1 errors, but you're going to now make more type 2 errors, right? So it's almost, yeah, it's actually very analogous to the concept of a hypothesis test. You're kind of playing around with those 2 errors.
Great, thanks for that. And then one more, you mentioned it briefly, but I think it's something worth highlighting again. I know I get this question frequently enough. So you recommended using the control chart submenu as opposed to going right into control chart builder. Can you just explain the relationship between control chart builder and then all of those individual options under the control chart submenu?
Yeah, so I could have done this same control chart I made using the control chart builder. And this acts just like our graph builder, where you drag variables into different roles. So if I pick up, let's say, line A, that's a numeric variable, and I put it right there, JMP's going to recognize, I'll close the capability, JMP's going to recognize, okay, you gave me a variable, a numeric variable. You didn't give me any subgroups. Well, in this case, the subgroup is size 1. So the default graph is an individual and moving range chart. And so it makes that same graph we made. And here are all those controls that I opened up when I was in the other platform. So at this point, it's actually the same. But the reason why I was kind of pointing this out is I think when you're teaching, you're not just going to say drag the variables into the row, because you're trying to teach the students like what's the right control chart for a particular variable. Do you have subgroups? Or, is it an X bar chart or is it an individual chart? Should you use a proportions chart? So for teaching, I think it might make more sense to actually pick the one. But JMP is recognizing what variable you just gave it. So if I gave it subgroups, it would have made me an X bar chart automatically.
Right. So then those individual dialogues, they're basically just shortcuts into control chart builder that means that students don't have to work with all those controls on the left if you don't want them to. Am I getting that right?
Yeah, you can turn that. You can turn that on or off. And if I opened up the IMR chart.
All right, great. Thanks,
Yeah,
Kevin.
if I click done, see, I'm back to that same graph as before.
Wonderful. I think we're good to continue.
Okay, so I'm going to open up a couple little data sets that I created to help that I think you can use to help teach the concept of, what are control charts. Okay, so this is a simulated data set. It's got 10,000 observations, and all of these data are a random sample from a normal distribution with a mean of 10 and a standard deviation of 1. In other words, this process is in control the entire time, right? Nothing is changing. The mean is 10, the standard deviation is 1 throughout the whole time. Okay. But if I go and I'm going to make an individual chart here of all 10,000 of these. Well, remember, 99.7 values will be within 3 standard deviations, and 0.3 will be outside of 3 standard deviations. So if you plot enough data, like in this case, 10,000, then eventually there's going to be a bunch of points that are outside the control limits. In fact, I created this other column here, which is just a little bar chart counting the number of inside and outside. Now, what I'm going to do is I want to see if I can get all this to fit on the screen here. Let's see. Put this here and here. Okay, I'm going to open up that formula again. Okay. All right, so let me move that up there. Hope I can get all this to fit. Okay. So every time I hit this apply button, it's going to generate 10,000 observations from that distribution, and watch. Well, you kind of have your students watch those numbers. See, there you go, 99.7, right? 0.3, that's the plus or minus 3 standard deviations. So you basically have your students, watch those, and also keep an eye down here to see the ones that are outside the limits. And so every time I hit apply, so this is indicating that even if you have an in control process, well, there's still a probability that observations will land outside it. So to the person that was asking that question about when would you maybe change the test, say from 3 sigma to 4 sigma or to 2 sigma, you can actually go and do that and start to see like, oh, we're actually being misled more times if we tighten up those limits. And we'll be making, so anyway, this is just a way to get students to understand that even in control processes, we'll eventually have data outside the control limits. And then I also created this other little data set that you'll have access to. And so I've got 3 variables here. This first one is just like the other data set I just showed you. Everything comes from a normal distribution with a mean of 10, standard deviation of 1. This one I just made a formula where for the first 10 observations, normal distribution, mean of 10, standard deviation of 1. And then from 11 to 17, the mean shifts up to 11. The standard deviation remains the same. And then from 18 onward, the mean drifts even further up and is now 13, 3 standard deviations away from 10. Okay. Then I have this, then I have this variable, which what I'm doing is I'm keeping the mean the same. So you'll see that the mean is 10 throughout the entire sampling period, but the standard deviation goes from 1 to 2 to 4. And then the last one is I'm combining both of these. So you'll see it goes from 10.1, 11.2, 13.4. So both the mean and variation are changing. Okay. So the first one's an in control process, and the other 3 are out of control process for different reasons. So I made an individual moving range chart. And so I can now take a look and say, okay, well, this first one is that in control process. So that's how this control chart looks. So I wouldn't be misled here thinking something's out of control when it's not. Here's the one where the mean is shifting. And I think you can all see that go like this, right? Now, eventually there's a point beyond. Oh, actually, you know what I'm going to do is I'm going to turn on all those tests actually, because what I want to do is have it help me point those conditions out. Okay. So here I'm getting conditions where things are going to be on one side of the center line. This one here is the mean is staying the same, but what's happening is the variation is increasing. So you can see it in the individual chart. You can also see it in the moving range chart, right? The variability is getting bigger there. And then the last one, we've got both the mean is shifting and the variation is increasing. Now you might look at this and say, well, nothing's beyond the control limits. I can see, the moving range chart, the higher ones are down the end. Oh, you know what's happening here? I actually should do something. If I go in here and make, oh, you know what? I actually have this done in a different data set. One of the things you can do is I can set up a column property for the control limits. And so this way, see, the control limits are based upon the data. So it's kind of a funny thing that as the process is out of control, causing more variation, it actually pushes out the limit. So it's kind of these things are kind of playing with each other there. I can set this up so all the charts are fixed with the same center line and control limits. So this actually would have been a better one to use, because if I do that, so everyone now has a mean at 10, lower control limit at 7, upper control limit at 13. And so this is making that situation more obvious now, because I'm not letting the control limits get pushed out. And so now we can see this is a case where that mean is both shifting and the variation is also increasing. We can see that there. So that was probably a better way to do it, is to actually fix the limits. So you may find these kinds of data sets where you can simulate stuff, make little changes and see if the control charts can pick up the little adjustments that you make. All right, now I'm going to open up a data set that has subgrouping. So this happens to be a semiconductor manufacturing process, and the key variable is this thing called etch rate. And I'm just going to do the analysis on one of the variables, but similar to the food manufacturing process, we've got different production lines, and etch rate is measured on each of them. Okay. Now the difference between this and the food manufacturing process is there's an idea of subgrouping. So basically what's happening is each time the process does a run, where wafers get kind of brought into the machine and they get etched, and then they move out, and then another batch of wafers comes in, and so there's a column identifying run. And so we've got run 1, and I think it goes to 40. Yeah, so there's 40 runs. Now for each run, 5 wafers are sampled. Okay, so you'll see for run 1, there's 5 wafers. For run 2, there's 5 wafers. For run 3, there's 5 wafers, and so on. And then for each wafer, so there's wafer 1, there are 4 measurements of etch rate made on that same wafer. Okay, so there's actually kind of 2 sort of levels of groups here. There's run, and then there's wafer. And so when I go to do a control chart of this, I don't want to just, well, I'll do a couple here. I don't want to plot individual values. I want to plot means and some measure of variability. So I'm going to choose the X bar chart, because that's the main chart, is the mean. So I'm going to put this in here. Now I'm going to do this 2 ways. The first way I'm going to do it is I'm going to make run the subgroup. Oh, there's another variable in here. The way this works is the process is recalibrated after, I think, 20 runs or something. Yeah, after 20 runs, the process is recalibrated. So there's a variable here saying calibration 1 or 2. So what you can do in JMP with control charts is you can identify something called a phase variable. So when I put that there and I click OK, what it does is it actually creates a pair of control charts for each phase. So I got phase 1 and phase 2. So you'll see each has their own center line and control limits. I mean, they're close, but they're unique. So this particular pair of control charts, this is plotting the mean of, let me move this over here so you can see, that's the mean of those 20 observations. So that's the etch rate on run number 1. And this down here is the range of those 20 observations. Now, my preference, I'm going to pull up the control panel, because now I'm going to have options. My preference is the standard deviation is a much better measure of variability than the range, especially in this case with 20 observations. Right? The range only uses 2 data points where the standard deviation will use them all. So I can choose to plot the standard deviation instead. And now this graph on the bottom is the standard deviations, not the ranges. So I've got the mean of each of those runs, and I've got the standard deviation of each of those runs. And I'm not going to turn on the test, but we can all notice that the means look pretty consistent. What seems to be happening is that the variation seems to be increasing as the runs go on. So there's more variability within the run. I'm going to close that because now I'm going to run it a different way. And this way I'm going to run it is I'm going to make wafer the subgroup. Now, the way I'm going to do it is I'm actually going to use this column just because it's got both the run and the wafer identified. So I'm going to use this, but it's basically the wafer. Let me put my phase in there again. Click OK. And so now the way this is done is this is a plot of the mean of the 4 measurements made on wafer 1 in run 1. And this is the range. And if I want, I can bring up the control panel and I can change that to the standard deviation if I want to use that instead. Okay, so now I'm tracking the mean of each wafer, the measurements made on each wafer, and the standard deviation of those measurements. So this is another way to subgroup. And if you kind of look at this going on, notice that as I move along, then the variability in those means, like the shifting from mean to mean, in other words, wafer to wafer, seems to be getting larger as the run goes on. And we also notice the same thing, the standard deviations tend to get larger towards the end. Now, when I teach control charts with subgroups, I like to use an example like this that has different levels of subgroups, so you can sort of get the students to understand that we're basically monitoring sort of 2 things. What's happening on average, like where's the central tendency, and then variation. But you might have different levels of variation, like within wafer variation, between wafer variation, within run variation, between run variation, and so on. I mean, we even have a phase variation, right? Phase to phase or within phase. And so basically that's kind of what's going on in control charts when you've got subgroups. So this can be a fun example if you don't find it too confusing for the students to have the concept of multiple levels of subgrouping. All right, now I'm going to close this one and move to control charts for categorical data, but just want to check in. I don't see any questions pending, Ross. I think we're pretty good.
Yep, looking pretty good. Just hitting about the halfway mark right now.
Okay, thank you. All right, so now what I'm going to do is I'm going to open up a data set where I can make proportions charts and counts charts. Now, I like using examples where I bring these both together because then you can see they're sort of tracking 2 different things. So this data set is about inspections on circuit boards. And so each row is telling us the sampling of boards. And so basically each row is a day. So on this day, 250 boards were tested, and this day 250 were tested, and so on. So it starts off with 250, but then changes. That's just kind of how life works. The goal might have been to do 250, but whatever, for different reasons that they weren't able to inspect that many each day. This column is of those boards that were inspected, how many are defective. So for day 1, it's 2 out of 250. Day 2, it's 3 out of 250, and so on. Day 16 is 11 out of 250. Day 21 is 7 out of 193. So to track this, which is how many defective boards there are, I'm going to want to graph a proportion, like 2 out of 250, 3 out of 250. And so that control chart is called a P chart. And so my outcome variable is defective boards. I have to tell it how many boards are inspected. I don't have a phase variable or I don't have any subgroupings going on, but if I did, I could add that. And I click OK. And what I'm getting is a control chart that's tracking the proportions. Okay, and we can all see that that at least there's a bunch of days here where there seems to be a large proportion they're outside the control limits. You might even argue, is this sort of going like that? Maybe that's possible. And this is where you're trying to get the students to understand that, well, what the natural level of variability for proportion is changes depending upon the size of the sample. And so that's why, when it's at 250, it's all the same. But then when I change from 250, well, the control limits are going to change with it. So if you were showing them that formula, right, plus or minus 3, and the standard deviation of a proportion, right, p hat, times 1 minus p hat over n square root, right? If you're showing them that they would understand why you don't have constant control limits. The other variables I have here, which is once it has a defective board, it counts the number of defects on that board. And so I've got 3 variables here. One is the total number of defects, and then I have it broken down into 2 types, solder defects or component failures. So these 2 columns add up to this one. Well, if counting the number of defective boards, the highest number it can be is 250, right? Because the board is either defective or it's not defective. But when you're doing counts, well, there are many thousands upon thousands upon thousands of opportunities on these boards, on each of these boards where there could be a defect. So the counts correspond to a Poisson distribution. So there's a different control chart. You don't want to interpret this as 12 out of 250. That's not what it is. It's actually on the 2 boards, there were 12 defects found. Now, if I was really doing this in practice, what would be nice to keep track of too is, like, are all these 12, is it 11 defects on one board and 1 on the other, or is it split 6? We don't know. But the appropriate control chart for this one is a U chart. And so basically, I'm going to put all 3 of these variables here. It's going to count the number of those defects per unit. Now, in this case, a board is a unit. This could be time. It could be like a physical area. Imagine you were looking at defects on a substrate or something, but in this case, it's boards. Okay. And click OK. And then now I'm getting a view of that count of number of defects per board. And these control limits are based upon the Poisson distribution. For the P chart, they're based on the binomial distribution. And again, we can see kind of the out of control conditions. And sometimes, you're trying to get your students to understand that a process being in control just means that it's stable. It doesn't mean it's good. It just means that it's stable. It's not changing. There's only natural variation. And an out of control, saying a process is out of control, means it's changing. So the change doesn't always have to be bad. So here's a case where this process is out of control because it looks like the number of component failures is remaining pretty constant, and then it drops way down here. So this is a case where the out of control condition is actually an improvement on the process, and you'd want to figure out, well, what's happening such that that type of defect dramatically reduced. So when I teach proportion charts and counts, I like to come up with a data set where I have them both together, because you can see that they're tracking similar things, but not the exact same thing. And they're often paired together like this. Okay, now JMP has, I'm just going to open up the menu so you can see. Okay, JMP has more control charts than the 4 that I just showed. I'm not going to be able to go into these, so I encourage you to take that statistical process control course that I pointed out in the resources, as well as just going to our help documentation. And so that course there and the help documentation is where you can learn about more of those control chart capabilities. Okay, so with that, I am going to move on to process capability. Now I'm actually going to open up that that semiconductor example again. Okay, so remember, we're measuring etch rate on different production lines. Okay. So those two concepts, control is about a process is stable, and capable is, well, how good is it? How well does it perform to specification? So for each one of these, I've got a lower and an upper spec limit. I set that up as a column property. And so now when I go and run process capability, oh, actually, if I ran the distribution platform, because I have spec limits saved, if you have spec limits as a column property, when you run the distribution platform, you're actually going to get the capability analysis done inside the distribution platform, which might be nice because maybe students are familiar with this platform, and then here are all the metrics. But I'm going to launch the actual process capability. Okay. And because actually what that distribution doesn't do is it doesn't really set up the subgrouping, which I want. I mean, it's using moving ranges for variation, but I really want to work it into subgroups. So the way you set this up is you put your variable in, or variables, and then for each variable you have there, you've got to tell JMP what the subgrouping is. And so what I want to do is I'm going to use that run and wafer. So this way each subgroup is the wafer. And then I click this button here. And when I do that, you'll see that what gets added is it's indicating what the subgrouping is set up to be. So that's nice, because if you have more than one variable here, you can set up unique subgrouping for each. And there's also all sorts of other controls, like if I have a historic standard deviation I want to use. There's distribution options. The default is normal. I'm going to open up an example where it does multiple ones. So I'm going to hit OK. Now I'm going to close these. I'm going to show that in another example. And so now I'm just going to open up the individual details report. So all the capability metrics are there. There's a graph of the data, spec limits. I've got the normal distribution superimposed. Oh, whenever you have a table at JMP, like you see these tables here, if you right click on the table, options appear. And so one of the options often is to pick which information gets shown. And so JMP will have a default set. Like for example, it's common to display this as parts per million. And so you can pick those if you want. So I'm going to say, for example, expected overall parts per million. And then now it just added that column. Now, if there's a table of information that you're like, I don't know what some of these metrics are, well, you click on the little question mark up here. And when you float your cursor over different pieces of output in JMP, I'm just going to click on one. And then what it's going to do is it's going to open up the help menu for that output in this case, which is capability analysis. And then I have the content to look at. I can see options, definitions. There's all my part per million explained. Again, you might see equations and formulas and examples. So you can direct your students to that too, so they don't get overwhelmed every time they see output. Now, one of the best features about the capability analysis platform that JMP has is this interactive capability plot. And this is great for teaching. So now let me just get that up to the, whoops. Oh, I do have to have that open. Okay, I just was trying to close some windows here, see if it makes it easier on the screen to, a little bit. Okay. So now this is an interactive tool where I can actually start moving around, doing little what if scenarios, like what if the mean is shifting, and you can keep an eye on those capability metrics, and or what if the variability is changing. So you can see how do those capability values change as this process does change, or maybe the spec limits are different. So I can move around the spec limits. Okay. and getting students to see like, well, what happens or what would it take to get a process to have a certain capability? And you might have to show that, okay, I got to get the process centered, and then I've got to get the variation small enough to achieve some kind of capability metric, like, to get the Six Sigma process, like, capability metric of 2. You can see what you need to do. So this is a great tool for teaching, I think, for sure. Okay. Now, I wish I had more time to like talk about each one of these, but I'm really just trying to give you an overview of JMP's capability so you can use in the class. So the other example I just wanted to pop up here is I'm going to do a capability analysis on 9 variables. And if you take a look at the data, you'll see each of these variables are on different scales. So they're not all on the same scale. And so if I run the capability analysis on these 9 variables, now I can see them individually. And I'm just gonna, so here's all 9, right? The same report I was just showing you in the previous example. But one thing I made this date up is notice Y9. Now, the assumption is a normal distribution. That's why I picked that for default, but clearly that's not a normal distribution. And so what you can do, and I'm going to go back and change it, but what you can do is you can pick different distributions for different variables. And so I'm going to click on Y9, and now I know what distribution is because I made up the data, but you would do the normal types of analyses to see like, oh, let me try different distributions and which one fits. But I deliberately made it to be log normal. So what I can do is say for that variable, make that the log normal distribution and do the capability using that distribution. So I can pick subgroups and unique information for each of the variables. But the reason why I wanted to show this example is JMP makes a set of graphs which allows you to compare everything. So it creates these standardized box plots. So even though all the data is on different scales, it standardizes it to each of the unique set of spec limits so I can actually compare to see which variables are within the spec limits, or they're centered. So, for example, this one here, that's centered within the spec limits, has low variability. This one's pretty low variability, but it's kind of pushing towards the lowest spec limit. Here's one that looks centered, but a lot of variation. And so this way you can compare performance. And then this graph up here is really nice because what it does is on the x-axis, it's plotting where the mean is relative to those spec limits. So ones that are centered, like this one right here, that's Y6, that's centered right there. So anyone that has the mean right on the center of those spec limits, those would all be kind of in this area right here. Any of the ones that are shifted, like this one right here, well, that's got to be, oh, there it is. That's Y5 right there. On the y-axis, it's plotting the variability. So the more variation there is, the higher the point is. And you notice that when you actually float over your cursor over a point, it actually pops up an individual. So now I can actually look at control and capability at the same time. Now, the reason I think stuff like this is really nice is I always find when you're teaching something, I always like using examples where you can compare and contrast many things. And so this allows you to kind of say, oh, this variable has got, really small variation, which is good, but it's off target. And then this one is on target, but it has way too much variation. Or this one looks good, but the process is unstable. Where's the one that's unstable? Like, oh, here's one here. The variation is good. It's within spec limits, so it's actually quite capable. It's pretty close to being centered, but you can see how that process is shifting and changing, so it's out of control. So I don't know. I always like when teaching is to have a bunch of variables because then you can kind of put together a whole range of situations all in one data set and compare and contrast. There's many more things that capability platform does, but again, for preservation of time and just because this is an overview, I'm going to move on to show you our measurement systems analysis platform. But before I do, Ross, anything that you think would be useful to mention at this point?
Nope, I think we're good. And with just 11 minutes left, why don't we give that time to MSA?
Yeah, perfect. All right. I'm going to close this up. All right. Okay. So for this data set, this is an experiment that was done to see how a sort of an inexpensive handheld measurement device is at measuring light reflectance off of a substrate. And so this variable here is the reflectance values that are produced. But what we also have is, and the column is called known reflectance, but basically the light reflectance using a very sophisticated kind of time-consuming, expensive piece of equipment was used to measure the reflectance on the substrate. Because the thought I want to do is not only do I want to study the variation in this measurement system, but I want to compare it to what, say, the truth is, or like I guess we'll call it the truth. Now, sometimes when I have data sets like this, I also like to create this column called difference. You don't need to do it, but then when you make graphs or do any kind of analysis, if you did it on the difference, then you would know, well, 0 means they're equal. If it's a positive number, it means that the measured value is above the known. And if it's negative, it means the measured value is below the known. So I sometimes like to actually do the analysis on the difference, because then it immediately shows you what is above or below the known measurement. You don't need to have a known measurement to do gauge R&R, of course, but this data set has that. And so the way the experiment was done is 10 sheets, 10 pieces of this substrate were gathered, and four operators here, measured each one of the substrates 5 times. And so these first 5 rows of the data set is Ying measuring sheet 1, and those are the 5 measurements, and then sheet 2. Now, this experiment was not done in that order like that. It was most likely done in a type of random order, but this data set is just organized that way. But you, if doing this in practice, you would know that you would incorporate some randomness. Now, there's 2 platforms in JMP that you use to study measurement systems. And well, one of them, this one here, is if you had attribute data, you have to use this one right here. Now, there is quite a bit of overlap between these two. So I can select either one of these, and I can almost get through various red triangle options, I can eventually see the same type of analyses I would get in another one. So one distinction is if you have attribute data, where you're, say, measuring counts or a binary outcome, you have to use this one. But if it's numeric, you can use either one. So I'm going to pick this first one here. Now let's set this up here. So my outcome variable is the reflectance. Known reflectance is my standard. My part, in this case, is those sheets. And the X variable, which is sort of, I want to compare that reproducibility. How well does this measurement device work across another variable? In this case, it's operator. But I could have more than one. And sometimes I have that. Like maybe I had 2 measurement devices and I wanted to try those out. Or maybe there were settings on those measurement devices. So I can put more than one there. There's options to select different methods. This is a set of procedures that was developed. I think it stands for evaluating a measurement process. They're trying to do the same thing. It's just different metrics. People have developed different metrics to use. I'm going to leave it as the traditional gauge R&R. I can set things like, okay, what's my sigma multiplier? And what is the nature of this experiment? This is a crossed experiment, but if I was doing, say, destructive testing, I could set it up as nested. So I'll leave that as crossed, and I click OK. And like everything you do in JMP, the report starts off with some initial output, in this case, these 2 graphs, and then you've got your red triangles to see more. And so the initial set of output here is The graph on top is plotting all of the measurements, so all 5 measurements each operator makes on each sheet. And the bottom is plotting the standard deviation. So this is where I can plot that, within sheet variability, the repeat measurements variability. Now, the fact that these are bouncing around, that's fine because each of the sheets are different, so they have different light reflectance. So then you start dropping down the red triangles to get more things. So for example, let's see what I might want to do. Actually, I'll add this to the graph. I'll show group mean. So now I'm seeing what's the mean of all the measurements made by each operator. And so this could be an indication that, notice that Yasmin's are quite lower than the others. So maybe that's identifying an issue there. Let's see what I want to do here. Oh, let me make some more graphs. So I'm going to pick some different graphs. Oh, here's a means plot. And so now I'm going to close some of these up just so I can move them farther up the screen. And so, this right here, that's the mean. That's the same as those purple lines I was just showing you right up there. Okay. Now I'm seeing the average for each sheet. Again, they're bouncing around because the sheets are different. This is a common graph, right, where we plot the average measurements on each sheet by each operator. And ideally, we want to see those lines all basically the same right on top of each other. See how you notice Yasmin, she's that mustard colored line there. And so you can see how hers seems to stand out as quite different. I can ask for things that are common, right? The variance components. So I can get estimates of variability. In this case, I can actually do, because I have a known standard, I can actually do this thing here called the linearity study. And so what it's plotting is the known reflectance down here, and then the bias, in other words, the delta between the measurement. And this one's interesting because you're noticing when they're working with sheets that have a high light reflectance, the values are high. Well, notice that the measurements, right, tend to be lower. And then when the light reflectance is low, the measurements tend to be higher. So it's indicating that there's some bias in this measurement system, but it's not constant across that range. Now, again, every time you do something in JMP, you're going to get another piece of output added to this report. And so here I am adding some familiar gauge R&R metrics, right? We talk about reproducibility. So the report gets pretty big. So remember, question mark. You're like, I don't know what variance components are. We'll click on that. And then it's going to direct you to documentation explaining what the variance components are and some of the options that JMP has in calculating them. Again, you just keep on dropping down the red triangle and adding to the report. Now, if I do this analysis, as I mentioned, sometimes I like to do these. Instead, I like to do it on the difference, because then if I did that, okay. So now by doing it this way, a 0 means that the measured value is equal to the known reflectance. So this is where you kind of see what's going on. We're like, oh, notice Yasmin's measurements, for some reason, she tends to get values that are mostly lower than what the standard really is. I mean, it's happening in some other cases too, but hers definitely stands out. So I just wanted to show that because that's why sometimes I think it's convenient to do it on the difference. Okay, huge topic. All 3 of these are actually pretty huge topics. So again, take advantage of our resources. We want to make it easy for you to use JMP in the classroom. So either use these resources to help you put your content together, or use these to supplement what you're doing. And maybe you direct your students to watch some of these recordings and lectures we have on various topics. So definitely take advantage of this to learn more. Hopefully what I showed you is getting you to see that JMP is a great tool to teach that particular set of topics in class.